Hello, good morning everyone. Welcome to the one-day workshop on quantum networking hosted by the Center for Network Intelligence here at IISc in collaboration with ECE and RBCCPS. Before we get started, I'll take a minute to tell you a little about CNI. Along with hosting talks and workshops like this, we also work on research projects in wireless networks. For example, you can see here we are working at AI and ML for health and infra for AI/ML, and not only in AI, we also work on wired and wireless networks such as multi-AP coordination in Wi-Fi networks and time-sensitive networks. And we also work on data center networks as well. I don't take much of your time. You can also visit our website if you are interested, and uh, if you think you can collaborate, and if you feel that these research interests you, please feel free to drop a mail, and you can also use this QR code to scan and drop your CV or resume. We will get back to you. And today's topic, quantum networking, connects very closely to the CNI's goal of advancing next generation networking technologies. And to take us to this exciting area, we have with us a researcher who spans several cutting edge areas of communication networks. It's my pleasure to introduce Professor Tirupataya Vasantam. He is an assistant professor of computer science at Durham University, UK. Before that, he was a postdoctoral researcher at University of Massachusetts Amherst. He earned his PhD from the University of Waterloo in Canada and his bachelor's and master's degrees from Osmania University and IISc respectively. His research focuses on stochastic modeling and performance analysis of communication networks with applications in quantum networking, cloud computing, and Internet of Things. Feel free to ask questions at any point. You can either raise your hand or interrupt in between. The professor said that he wanted to make this as session as interactive as possible. Over to you, Professor.
Still preparing slides, so I will distribute slides later. Okay, and please feel free to ask questions if you have any doubts in between. Okay, um, so first I would like to share some resources if you are interested in more. I basically my background is actually classical networking. I have started working on quantum networking 5 years ago. So I'm still learning this field. So I will explain what I learned so far. Okay, these are basics only. Um, and since this is an interdisciplinary field, it actually requires tools from various groups. For example, you need expertise from quantum devices, you need expertise from classical networking, you need expertise from quantum computer science and so on. So if you want to learn more, uh, there are some very good online lectures. These are given by people who are working on this field for almost 20 years. Okay. Okay, so he is a pioneer in this field. You can find these lectures on YouTube. Okay. Um, so this is also another lectures by Umesh Vajrani from UC Berkeley. Okay. And also So if you are coming from different backgrounds, say communications or signal processing, so initially it is difficult to read textbooks written by physicists. So they use terminology which is difficult to follow. Okay. So often it becomes easier to read materials written by some electrical engineers or computer science people, because they do not use physics terminology too much. Okay. So there are some textbooks which can be easily followed by engineering community. Okay. So this is a textbook, quantum communications by and this is available on archive. So okay. So this is digital. You can find digital copy online. And also quantum computation has been there for many years, but quantum networking is very new. For example, the progress is has only started around 5 years back. Okay, there are physicists working on this field, but the progress from computer science and electrical engineering departments have started just recently. Okay, so there are very limited books. The only textbook on quantum networking is again by Radney Van Meter. So he has been working on quantum networking for almost 25 years. So he is one of the leading figures in this topic. So this textbook is mostly like simulation based, numerics based. There is not much analysis in quantum networks, because still this field is new. So we are trying to develop, people are trying to develop analytical techniques to design algorithms and analytical methods to develop quantum networks. Okay. So these are good references if you want to start learn more on this topic. Okay. There are good survey papers. Okay. So you will see that there is something called entanglement in quantum mechanics, and this is a quantum state that is useful for most of the applications of quantum technology. Okay, in quantum networking, most of the time our focus is how to distribute these type of quantum states effectively in quantum networks. Okay, so this paper gives a overall progress on this topic. And also this paper is written by people from a company in quantum networking company in Boston. So you will learn more some hardware details as well as some theoretical details. Okay. So this is a paper from hardware communities. So these are, it has a very lengthy authors. So it includes people from physics community, science community, and so on. So it's a very detailed document, almost 40 pages. So it explains details about quantum networking, including hardware details, what are qubits, and it also explains some quantum devices and so on. So these are two very good survey papers when you start learning about this field. Okay. So I will now first begin with some motivation. Okay. Why this field is important, right? Okay. Why this field is important. So we have seen that our computational power of our device, electronic device, has increased over the years because the transistor size has decreased. Therefore, we were able to place more and more transistors on a single chip. Therefore, we were getting better computational power. But once transistor size becomes like an atom, okay. Once a transistor reaches to atom level, then the correct theory that we need to use to study transistors behavior in chips is quantum mechanics, because quantum mechanics is the right, according to physicists, is the correct theory to study in nature. So therefore, quantum mechanics is correct theory for small particles. Okay. On the other side, our current computers, they are built assuming that the classical mechanics is correct. Okay. But the classical mechanics is a good approximations only for large entities like say humans, animals, or vehicles, and so on. When you are studying small atom level particles, you need to use quantum mechanics. Okay. Therefore, in future, if you reduce transistor levels sizes further, then you must use quantum mechanical theory to understand computation. Okay. And Richard Feynman is the first person to conjecture that. So Richard Feynman explained the importance of okay. So in 1981, in a seminar, he explained that because nature follows quantum mechanics, okay, you cannot study correctly the nature using classical computers. That is that the computational power of classical computers will never be enough to study exact the nature. For example, if you want to study some behavior of some particles in physics, you must use quantum mechanics. Okay. So that was his conjecture. In 1981, he explained why we need to develop computers that work based on principles of quantum mechanics. Okay. And then there was some breakthrough results after some time, which actually increased the interest in this field. For example, in 1984, BB84 protocol was developed. This is like for QKD, quantum key distribution. So essentially, when we send our messages across internet, we send a message. We actually encrypt some secret keys, and we send the messages on the internet. Okay. So this is the first protocol showing that if you send encrypted information using this protocol, your data will be more secure. So if there is some eavesdropper, you can easily identify that eavesdropper who is trying to capture these secret keys. Okay. And then in 1991, in 1994, so Shor's algorithms was developed. So Peter Shor is one of the most pioneering quantum computing researcher who is a professor in MIT. So he showed that if you have a quantum computer, suppose someone builds a quantum computer, then he showed that one can easily factor large integers as product of two prime numbers, which means that based on this idea, all our current cryptographic systems have been developed. Assuming that our any classical computer or even supercomputers, they will not be able to find factors for any given large integer. So that is a key idea when we are using our cryptographic algorithms. Okay, but if someone develops quantum computer, he showed that using polynomial time complexity, you can find easily factors for any large integer. So which means that all our current cryptographic systems will not be secure if someone has developed a quantum computer and has access to quantum computers. So therefore one has to actually develop improve cryptographic algorithms to make sure that even quantum computers cannot decode those encrypted messages. Okay. So this is one another breakthrough result. And then in 2016, okay, so China has implemented China's QKD. So here QKD means quantum key distribution. So China's QKD experiment using satellites. Okay. So after 1994, there was some progress, but still people were not believing this technology. In 2016, the China has shown some experiment wherein they were able to distribute quantum bits using satellites between two nodes that are separated by around 1200 kilometers. Okay. And after this breakthrough result, then many countries and researchers have shown interest in this field. So most of the countries, Japan and all other major players, they have invested a lot after this experiment because China is now very advanced in this field. Okay. You will see that even satellites will play a significant role in developing quantum internet. Okay. The main reason is that in the space, after 500 kilometers, it is completely vacuum. So if you send quantum bits, there will not be much interference or noise in the free space. So because of that, the photons or any qubits can travel over long distances. So therefore, if you want to connect two nodes that are living in two different continents, we must use satellites. So, okay. All initial, at least for 10, 15 years, 20 years, once quantum networking becomes practical, satellites will play a significant role in this field. Okay. So now I will start with introduction, topic 1. Okay. Is this visible this side? No. Okay. I will use this. So qubit is essentially a quantum bit, which is the basic unit of quantum information. Okay. And it is essentially a superposition of two basis states. Okay. Okay. So here this notation is ket. This is notation is called ket, and this notation is called bra. Okay. So these are Dirac's notations that we use for representing quantum states. Okay. And here alpha and beta are complex numbers. Such that the modulus of alpha square plus modulus of beta square is 1. Okay. And 0, 1 are the basis states. I mean, Okay, so these are similar to classical 0 and 1. Okay, so mathematically this is how we represent quantum bits. Okay, now in experiments in physics, we can encode quantum information in several ways. For example, we can use photon polarization as qubit. For example, vertical polarization is like 0 and horizontal polarization is like 1. Okay. So photon means essentially very small. If you reduce the intensity of the light, the smallest particle is photon. Okay, and it has some wave behavior, and it will have some polarization which has different directions. Okay, so now any polarization is essentially superposition of these two horizontal and vertical polarization. Okay, and suppose if polarization is in some other angle, then it will be a superposition of 0 and 1, similar to how we write vectors in two-dimensional space as a combination of horizontal line and vertical line. Okay, and similarly we have electron spin. Okay, and we can also use some energy levels of atoms. Okay, so in practice, there are different companies which are trying to build quantum computers. They use different atoms. For example, some atoms have some good properties and some bad properties. For example, some atoms can be stored for long duration and they can be easily manipulated when we perform computations, and some other atoms will not have such good properties. So every atom has some good properties and some bad properties. So different companies are trying to build quantum computers based on their own interest. They choose different particles and then they develop quantum computers. Okay, so these are 3 examples, but there are several ways how you can represent information, quantum information in practice. Okay, and why do we use complex numbers? There is something called these horizontal and vertical polarizations are examples of linear polarization. There is something called very complex property which is circular polarization. Okay, circular polarization actually has two. For example, when you have this complex number alpha, it has two real component indicates some property and imaginary component represents some other property. Okay, in circular polarization, you will have very complex behaviors. So to exactly represent circular polarization, you need complex numbers as coefficients here. Okay, so this is how physically we can represent qubits in practice. Okay. Yeah, yeah, yeah. Yes, yes. So they choose different atoms, different materials. For example, I do not know exactly their behavior, but different companies have different atoms and they have different behaviors. For example, another company called IonQ. They use trapped ions. Ions. There is some company called Quantum. They use photons themselves. Photonic device. Everything is photons. Fiber. They are trying to build quantum computers just using photons. Okay. Yeah, yeah, yeah. Okay. So I do not know exactly full details, but every company has their own justifications why they are using qubits. But the progress is still in initial stages. Okay. So now, so this is a mathematical representation. We can also write these qubits in vectors, and then we can try to use Hilbert spaces and so on. Okay. So vector notations. Okay, we can use vectors to write qubits. For example, we can use 1 0 for 0 state and 1 can be used using 0 1 state, and then this state psi becomes like alpha beta. So, this is a vector notation for a qubit. Now, if you have like n qubits, since each qubit takes 2 dimensions, n qubits means they will take 2 power n dimensions. Okay. Now, once we define qubits as vectors, we can write actually inner product of qubits, to understand how those qubits are related to each other. So, that inner product is, suppose if you have, suppose if you have 2 qubits x and y, okay, then their inner product or scalar product is denoted by yx, which means essentially okay. And here this, how do we get this y? Suppose if y is this notation, say y1 and y2, essentially bra y corresponds to y1 star and y2 star. So, essentially we need to apply conjugation and pose. So, now this indicates scalar product of these two vectors, okay. And we say that two vectors are orthogonal if this inner product is 0. For example, here 0 and 1 are orthogonal to each other. If you take inner product of these vectors, you get 0. Okay. Sorry? Yeah, so these states are basis states. Basis state in 2 dimensional space. Using these two vectors, you can write any other vector. So, in basis means they should be orthogonal, they are orthonormal set. Yeah, okay, I am not going to explain that. There is something called Bloch sphere in quantum mechanics. So, which is 3 dimensional space, although here we have 4 components, you can actually translate that to another system which requires only 3 components. Okay, and so then say a single qubit can be represented in 3 dimensional sphere. Okay, so it will take some time, so I am not going to explain that. Okay, but suppose if alpha beta are real numbers, your 2 dimensional space is enough. Okay, this one here, yeah. So, so this is ket y. So, ket y means this row vector, and this is okay, this is, sorry, this is bra y, and this is ket x. Ket x means is a column vector. Okay, so here ket x is essentially something like x1 and x2. Then it becomes part of this column vector, this row vector. Okay. So this is a short form for this notation. Okay. So this is called inner product. So this notation is called inner product, and we have something called outer products. So outer product you mean multi-qubit quantum states? Yeah, I will explain. So outer product is essentially is this one. So this is outer product x and y. Okay. So this is now this will become matrix by 2 matrix. So this is outer product. Okay. We will use this outer product in some way. I will explain later. Okay. So here I have explained that here 0 1 is orthonormal set. Okay. So orthonormal means each of their length is 1 and they are orthogonal to each other. So how do we define, say if there is a quantum state x, so the norm of x is essentially defined by inner product of x with itself, okay, and then we take square it. So this corresponds to the length of qubit, and we always assume that this length is 1, so they normalize qubits, and so this length is always 1, and essentially the length of 0 and 1 state is 1, but if you take inner product of 0 and 1, then that inner product is 0. This is the basis for 2-dimensional space. Okay. Now we can also write qubits in any orthonormal set. For example, you can write psi using some basis u, basis element u, and some other vector which is orthogonal to u. Okay, so u and u perpendicular. So if you take inner product of u and u perpendicular, it's 0. So we can write quantum qubit in any basis state. Okay. So I will explain photonics how they prepare such states. Okay. So there are some photonic filters. So by orienting those filters in different angles, they can prepare qubits with different basis states. Okay. So now we will. So there is an important basis which is called. So here we call 0 1 as standard basis. Okay, this is the standard basis. They call it as standard basis. And Hadamard basis, there is another one which is called Hadamard basis, which is essentially a plus state and minus state. Here plus means it has angle 45 degrees to x axis, 0 state. So these two states are orthogonal to each other, their length is 1. So they also form a basis for the 2-dimensional space, and their set is called Hadamard basis. So same definition actually extend to multi-qubit quantum states. So single qubit means it is essentially it indicates the property of a single particle like photon, electron or neutron and so on. Multi-qubit quantum states means it is a joint behavior of many particles. For example, you might want to study what is the behavior of 2 different photons and so on. Okay. So it corresponds to joint behavior of multiple particles. Okay. So for example, so we can take a 2-qubit quantum state. That 2-qubit quantum state could be superposition of 4 different basis states. Okay, such that this modulus of alpha 1 square plus modulus of alpha 3 square plus modulus of alpha 4 square is 1. Okay. So here 0 0 means that both photons they are in horizontal polarization, or 0 1 means one photon is in horizontal polarization, another photon is in vertical polarization. Okay. So this is an example for 2-qubit quantum states. Okay. So I will explain why we need to have this constraint. So this essentially indicates some probabilities with which when we observe these states, we get 0, 0 with probability modulus of alpha 1 square and so on. So I will explain this in later. Now if you take any qubit quantum state, okay. So we will have how many basis states will be there in any qubit quantum state? 2 power n, right? So you will have like k is equal to 1 to 2 power n. So we will have alpha k, okay, and we will have some quantum basis state xk, okay. So here xk belongs to like starting from all zeros to all ones, okay. So which means that any quantum state is a superposition. Sum is essentially called superposition. So there is some interference across these basis states, okay. So this sum is called superposition, and this quantum state, a single n-qubit quantum state, will have some information about all these basis states with certain coefficients included in this superposition, okay. One of the key property of quantum states that is used in quantum computations, okay. So there are multiple properties which actually help us in getting better computational power. So this is property, okay. So again the constraint is that uh, k equal to 1 to 2 power n modulus of alpha square should be 1. So this is a constraint on these complex numbers, okay. Mm-hmm. Yeah. So kt is essential means that it is a qubit. It's okay. So, yeah, essentially if you take so you need to reverse here. Yeah. In 4 qubit you will have 16 combinations. Uh-huh. Yeah. Alpha 1. So then, okay, then you have to use this notation. Then again you will get like this. Yeah, and each qubit takes 2 dimensions. If you have 2 qubits, then it will require 4 dimensions. Yeah, I will explain a little bit later. So just to make sure that, so when you observe quantum states, so you will see different outcomes, and the probability that when you sum over all those probabilities of getting different outcomes should be 1. So this normalization is required to get that the probability is summed up to 1. Okay, total probability is 1. So I will explain a little bit later. Okay. Mm-hmm. Yes. So for example, okay, so here for example, if we write 0, 0, so we can use 1, 0, 0. So we can use any vectors. We just need to make sure that they are orthogonal to each other, and you can. But once you choose some particular way, you have to stick to that way. For example, we can choose 0, 0 in this way. 0, 1 could be this one. Okay, and 1, 0 could be, and 1, 1. Okay, 1, 1 could be like 0, 0, 0 and 1. So this is the 4 basis vectors that can be used for 2 qubit quantum states. So this now the superposition of these 4 bases will lie in 4 dimensions, and that vector space is complex vector space. So complex vector, 4-dimensional complex vector space where every element is complex number. Okay. So I will explain why we can why current classical computers cannot be used to study quantum mechanics. Okay, suppose we take ket essentially it is going to be row vector and taking complex number. So here I chose 1, but if you add these coefficients, then it will now psi will become like alpha 1, alpha 2, alpha 3, alpha 4. Now bra psi is essentially taking row vector and complex conjugation. Yeah, yeah. So bra psi.
Basis won't change, it's the alpha 1, alpha 2 that will change the bra and ket form.
Yes, essentially it will become row vector. Now basis for these type of quantum states, you will be essentially going to row vector, like just taking row of transpose of these vectors will be the basis for bra notation. Okay. So I will explain now why our classical computers will not be useful for studying nature. Okay. Suppose we take 300 particles. Okay. So these 300 particles could be our proteins. Suppose if someone is trying to develop some vaccine, suppose if he needs to study behavior of some 300 proteins in our body, then we need to use quantum mechanics to study what is the behavior of those 300 proteins. Or in physics, if someone is studying some electrons or photons, their joint behavior should be 300 qubit quantum state. Okay. So 300 particles means we need 300 qubit quantum state. Okay. So essentially we need 2 power 300 basis states, right? So these are the basis states, 2 power 300. Okay. So now if you take psi, okay, this psi in this psi, we go up to 2 power 300, and we have alpha k and xk. Okay. Now in classical computers, say suppose that these basis states corresponds to some okay, there is some some atom which stores this basis information. Okay. Then how many say suppose that this is state. Okay. And you need 2 power 300 transistors to indicate each of these basis states. Okay. So in total we would need 2 power 300 classical states. Okay. And suppose that each of these classical states is represented by an atom. Okay. Okay. But the total number of atoms in universe total are 10 power 82. Roughly they are 10 power 82. So total number of atoms in universe. Okay. So even if we indicate every basis state by some atom in classical computers, we would require 2 power 300 atoms. But the actual available number of atoms are only 10 power 82, and major result is that 2 power 300 is actually greater than 10 power 82. So even if we use every atom available in the universe to represent some classical state, we cannot write precisely the joint behavior of 300 particles in classical. Okay, because the total number of atoms that you choose from the universe will be less than the required number of base states. Okay, so that is our classical either supercomputers or any computers, they will not be able to precisely study 300 proteins behavior or 300 electron behavior. What people can study, but that will be only some approximation, it will not be accurate. Okay. So that is this is the reason Richard Feynman said that classical computers will not be good enough to study nature, because he is physicist. So he wanted to study say some he wanted to simulate some physics particles behavior. So he cannot simulate physics particles exactly, in classical computers because of this reason. Mm-hmm. Mm-hmm.
How exactly
Okay, so suppose if there are interactions among these particles, okay, if they are say independent, so if you take product of so every particle requires one qubit, right? Say psi type, say suppose some state y which is like alpha 0 plus beta 1, right? Now if you take product of these type of states 300 times, then you in the total representation you will get 2 power 300 basis states. Okay, so even if you use some atom to for each of these basis states, you will require 2 power 300 basis states. So here suppose if you take say all zeros, that means that all these particles they are in ground state or something. All ones means that they are all in excited state. Okay. And so in this superposition you need to have all these basis states simultaneously in exact representation of qubits. So this is the exact behavior of 300 qubit quantum state, and so this exact representation requires 2 power 300 basis states, and then we need to multiply with them their behavior with some complex numbers, and then we take superposition in this manner.
Sir, one more thing, sir. Yeah, you are saying that this solution is actually a viable solution, but one more thing is, sir, when you collapse it, you state in one of the states. So even for suppose to get the probability distribution, so for even for 2 qubits we need at least 1000 runs. So if we want to get an idea about 2000, say 300 states, so how many times you have to run and collapse the states? So that's also puts a limitation in the
Yeah. So when you are computing probabilities, yeah, you need to run it many times.
Yeah, so exactly. So if there are 2300 states, so if we have to get the probability, we have to use the law of large number.
Yeah.
But the n has to be very large.
Yeah.
So is our
So that is also another limitation, right? So you cannot compute these probabilities.
It's a limitation for the quantum computers too, right?
Yeah. But classical computers, of course, they will not be precisely, they will not be able to compute these things. Quantum computers also will have some limitation. As the number of qubits increase, of course the complexity will increase even in quantum computers.
More than 500 qubits, like what they show on their website. Like,
Yeah, 500. Yeah.
so have these calculations been tried there?
Yeah, so they have tested some calculations. Although there are 500 qubits, but the number of qubits that they use for actual computations are less. Okay, so they do not use all the 500 qubits. Okay.
They don't use or they cannot use?
They cannot use. So some of them they use for some control information, something like that. So they have some physical qubits, some logical qubits. So they need some error correction and so on. So they want to use all the qubits for computations.
So essentially, at which stage are we right now?
Something like 30, 40 qubits are used for actual computation. Okay, so the error correction is also another major drawback in quantum. So it is still under development. Okay. So if error correction improves, then our computation will increase further.
Okay. So for this, we'll need 300 logical qubits.
Yeah. So this is essentially the basic quantum state, 300 qubit quantum. But if you are using this type of qubits for computations, for example, in error correction we have repeater codes. So one logical qubit is mapped to like say 10 actual qubits.
Okay.
To get some advantage during error correction and so on. Okay. As I said, I am just a classical networking person, so this is my understanding so far. Okay, so I cannot explain too much into devices, quantum devices, and those things.
You said these qubits cannot be represented, and because of like 10 power 82, we have a limitation, so we cannot represent all the qubits. So I assume assume that classical computers, whatever they are, they use the approximations of quantum networks. Am I correct?
Yeah, yeah.
And if so, how bad are they? Are they bad? And if so, how bad are they? Those approximations.
So essentially, if our classical bits, for example, transistor sizes become smaller and smaller, you need to use quantum mechanics. So I don't know about what is the limitation of supercomputers and so on, because I'm not from that community.
Okay.
But it seems they will not have enough representation for all these 2 power 300 basis states. Okay, because that is more than total atoms that we have in the universe. Okay. So I will now explain measurement principle. So we have this single qubit quantum state in this manner. So suppose there exists some quantum state. Suppose someone wants to know what is the state of this qubit. Okay. So then that person has to perform measurement. Okay. Okay. Using a basis. Okay. So essentially, when we say we are doing some measurement, essentially sending this photon through some photonic devices. I will explain. And so when we are measuring, we need to choose certain axis for for measuring devices. So we can place that measuring devices axis in any orientation. For example, I want to measure this quantum state in standard basis 0 and 1. Okay. Then this quantum state psi. So upon measurement, okay. So if you are doing measurement, it collapses to either 0 or 1. So this one becomes 0 with probability modulus of alpha square, and we get 1 with probability modulus of beta square. So if you are doing measurement, then you will get 0 and 1. Suppose if eavesdropper, if there is some eavesdropper who tries to know about this quantum state, he needs to measure. Okay, if he measures, then the psi actually collapses to either 0 or 1, which is completely different from original state. Okay, so the moment if the state collapses to another state, you can identify that someone is actually trying to manipulate our original quantum state. So this is a measurement, and physics community doesn't know why this happens. So this is a mathematical representation for what they observe in experiments in labs. Okay, so most of the quantum mechanical properties have been shown to be valid in experiments, and for all those works, there was a Nobel Prize given to 3 people who showed fundamental results in quantum mechanics. Okay, so this is the basic principle. And for example, here we can also choose to measure in different bases. Okay, for example, we can measure in Hadamard basis, plus and minus. Okay, then we will get. So we need to translate this superposition into a superposition of plus and minus states in order to estimate the correct probabilities. Okay, so for example, here in this, and we might get say this with probability, so say suppose some alpha plus square, and another one with probability beta minus square. How do we translate? So we need to use the definition of plus and minus. Okay. So using these two states, we can write and plus and minus state. So you can show that 0 is essentially and 1 is essentially this state. And then by substituting this into this superposition, you need to find the exact coefficients, and from there we can compute what will be the probabilities if you measure this quantum state psi using some basis. Okay. So the basis that you use for preparation could be different from the basis that you use during measurement. Okay. Yes. Yeah. Suppose you got to here 0. If you measure in 0 1 basis, you will again get 0 because the coefficient for the other one is 0, right, in this case. So with probability 1 you will always get 0 if you still measure again 0. Okay.
With the Hadamard, one of the Hadamard bases, right? It will collapse to a combination of
Yes.
0 and 1.
Yes.
And then next time I measure with like a 0 or 1.
Then you will get both 0 and 0 with some probability, 1 with some other probability.
Okay.
So suppose if you measure this, right, with the 0 1 basis, you will get with the probability of 0 and
No, so let's say I first measured with the basis of 0, right? And let's say it collapsed to 0, okay? And next time I'm measuring with one of the Hadamard bases, plus or minus.
yeah.
Then it should collapse to either plus or minus, right?
Yes. Yes.
So then that means it's this thing is changing, right?
Yeah, if you choose different basis, it will change.
Okay.
If you again choose 0 1 basis, it will not change. But if you choose different basis, Hadamard or maybe some other basis that lies at this angle to x-axis, you will get different outcome.
Okay, so that means let's say first I measure with 0 basis, then with a different basis, and then I come back again to 0 basis. It is possible that it will change.
Yes, yes.
Okay.
So I will explain simple terms. Suppose there is a polarization, photon polarization, that has angle, that has direction horizontal. Okay, and we have some device called filter. Okay, so this is a polarized filter. Okay, so we can place this filter in any angle. For example, this angle is theta. Okay, and then once this photon passes through this filter, the polarization will actually lie in this angle theta. Okay, and then we will place some detector which will actually detect this photon. So this is actually capturing this for example this state. Suppose if theta is 0, then this photon will completely pass through this filter. But if because if theta is, say suppose if theta is 45 degrees, then we get this Hadamard state, and for example it could be plus state here. So we can get polarization in any direction by placing filters in different orientations. And then how measurement means, essentially we need another device called beam splitter. So this beam splitter has some axis. Okay. Okay, so this is another photonic device, beam splitter. So this has, I'm assuming that this has horizontal axis and there is this vertical direction. So this, I mean, So this is just my understanding. Okay. So we are sending this photon through this beam splitter. Then this beam splitter passes through this device with some probability, and it will have horizontal polarization. It will pass through this direction, and with some other probability it will go in orthogonal direction, and this direction is the orthogonal direction. And then this photon, whenever it passes through in the perpendicular direction, you will get vertical polarization. Whenever the photon reaches this detector, then this detector can realize that there is a photon coming in this direction. Okay, so these detectors will click whenever photon hits that device, and it will give a hint that photon has reached this detector, because this is the measurement mechanism in practice. Okay, so we will use this also in entanglement distribution and explain later. Okay, so this is the measurement principle. No, so it is exact state. So you will, if you send a qubit, you will get some qubits, either say for example either 0 state or 1 state. So now if you want to compute probabilities, you many times, maybe 10 times or 100,000 times, and if you compute what is the fraction of the time it reaches this detector, that fraction actually coincides with this alpha 0 square, this alpha square, modulus of alpha square. And similarly, what is the probability that it will reach 1? This detector will coincide with probability modulus of beta square. Okay.
Like alpha and beta are complex number, and we are calculating probability.
Yeah, complex number will not come. It collapses to either 0 state or 1 state. Now complex numbers disappear. They actually play a role with what probability these photons appear in different detectors. Complex numbers only influence probabilities.
I mean, by the statement, like complex numbers plays in probability, so like that's why like there will be 4 probabilities in that case, because alpha have 2 and beta has
No, modulus, right?
Yes.
So here modulus, so this has one real component, one imaginary. So this is modulus of alpha square. So this has two components, this has 2 components.
Alpha square is a probability. Alpha beta square are probability, right? So
No, modulus. So here constraint was that modulus of alpha square plus modulus of beta square should be 1. This was the constraint that we started with.
yes.
So and now modulus of alpha square corresponds to what is the probability that if you measure you get 0 state, and this corresponds to what is the probability that if you measure you get 1 state.
But the origin of alpha and beta is some complex number.
Yeah, so alpha has some real component. So for example, it could be some x alpha plus I some y alpha something. So we will take modulus of this number.
So then where like what this x and y will then represent?
This is part of this probability. So this is actually measurement principle. So this is from quantum mechanics, and they observe that in labs this is what happens. So if you take what is the fraction of times you get photon at this detector will coincide with this modulus of alpha square. Okay, and I mean, even physicists cannot explain why it happens in this way. So this is a mathematical way of explaining these quantum mechanics. Okay. Yeah. Yeah, if you repeat the same experiment 10,000 times, that fraction will modulus of alpha square and modulus of beta square. Okay. So next I will explain entanglement.
Sir, should the source there be a single photon source?
Yes, single photon.
Because how would you differentiate a beam of vertical and horizontal polarizations from that experiment?
Vertical and horizontal.
Yeah.
So this is I mean in labs they can prepare, these photonics people they can prepare. So they have some device which can actually generate photons having certain polarization. Okay. So now another important property in quantum mechanics is that having strong correlations among different qubits in a multi-qubit quantum states, and we do not have such correlations in classical mechanics. Okay. And those quantum states are called entanglements. So essentially, suppose you take some n qubit quantum state. So you cannot write this as some okay, say this is 0 beta alpha 1 beta 1 for any alpha 1 beta 1. Okay. So what it means that if you take, so n qubits, is there any question? So okay, so if you take n qubits, means that the behavior of n particles, and suppose that their behavior is independent of each other, they are not coupled with each other, there are no interactions among them. So this, now this corresponds to the state of the first qubit, and similarly we will have second qubit, and similarly we will have the nth qubit. Okay. So this is a product of these different qubits. Okay. So this is essentially a tensor product, means that the first component corresponds to the first qubit, second component corresponds to the second qubit, and so on. Now there will exist many n qubit quantum states in such a way that if you give any values to these coefficients alphas and betas, you will not get this quantum state. Such states are called entanglements, meaning that whenever you talk about these n qubits, you need to talk about them jointly, you cannot separate them out. Okay. Such states are called entanglements. Now because of these correlations, we can actually use in various applications like cryptography, security, and so on, because there is some synchronization among these qubits, some information is there across these qubits, therefore you can actually couple them. Okay. And one example is called, this is a Bell, this is also called Bell state. So you cannot write, this is an entanglement, you cannot write this as a superposition of as product of two individual qubits. Okay. This is called entanglement. Yeah, we can stop.
Excuse me, a small announcement. So we are going to have a small photo session at the entrance of the main building. Please join us. And then we will meet at 12 o'clock, within half an hour, 12 o'clock.
Okay. So these are some intermediate nodes which are like quantum switches and quantum repeaters. We will see what are those, how they work. And so essentially many applications require creation of entanglements, say for AB, and then for example they can use those entanglements for some quantum communication or even for distributed computation and so on. So how do we distribute entanglements? So we need to create distribute entanglements in such a way that A gets one qubit, okay, and B gets another qubit of the 2 qubit entanglement. So this is what essentially quantum networking, we want to send qubits from one place to other, we want to create entanglements, and this requires routing, scheduling, how do we use each of these devices effectively in networking. Okay. So now I'll go to the next topic, topic 2. So I will not go too much into quantum computing. I will just give a brief introduction. Okay. Okay. So essentially, quantum theory or quantum mechanics postulates that quantum operators should be linear. So which means that suppose if U is an operator and okay, so this is a linear operator. Okay. And further, unit length quantum state should be mapped to unit length quantum states. Okay. So which means that if you take norm of any quantum state, that norm should be 1. Okay. And so physicists, they believe that the nature should have these properties. Okay. And using these two properties, you can show that, you can prove that suppose if the inner product of x and y is 0, then the inner product of ux uy is also 0. Okay. So these two properties, linearity and preserving unit length, will give us this property, which means that if the two vectors are orthogonal to each other in the beginning, and after applying transformation, they will remain orthogonal to each other. Okay. So here ux uy is essentially like it is something like this. So this is taking this is complex conjugate and transpose, so it becomes like this. Okay. And here this one okay, so here there is also transpose here, so transpose. So this one is identity. So you will preserve this inner product only if this one becomes identity. So which means that all quantum operators should be unitary. So for example, if x and y are same, okay, so then this will become 1 if the middle guy is unitary. And if x and y are orthogonal to each other, then the inner product becomes 0 if this middle guy becomes identity operator. So which means that all quantum operators, so from these properties you can show that all quantum operators are unitary. Okay, so which means that u dagger u is identity. So here u dagger is essentially taking u conjugate and transpose. Okay. Now from here you can show that inverse of u is essentially u dagger, right? U dagger is essentially taking complex conjugation and then transpose. Okay. So from these properties you can show that u dagger is essentially inverse of u, which means that all quantum operators are reversible. So from this we can come to the conclusions that all quantum operators are reversible. Okay. So when I say operator, means it is some mechanism which translates the quantum state to another quantum state. For example, this could be physical, like we might use some photonic devices to apply quantum operations, or we can use electromagnetic fields, laser light, electromagnetic fields to change the quantum state. Reversible. So for example, if you apply ux, okay, so y is ux, right? So you got ux. Now you can go back from y to x. So which means that you can get back x by applying u inverse of y. So which u inverse means essentially u dagger. So all quantum operations are reversible, and in classical computations there are some operations which are not reversible. For example, AND operation, if you give input 0 1, you get output 0, but you are not sure whether the input is 0 1 or 1 0. You cannot know what is actual input. So in classical computation there are some reversible operations. So this is also another property which actually helps us in scaling up quantum computations. So you can go back, okay, to initial states. And do you think measurement is a quantum operator or not? No, right? So once you do measurement, you go to some state, but from that state you cannot go back to the initial state, because you will lose information about these complex coefficients. They will not appear. They will only influence these probabilities, how you observe different outcomes. Okay. So measurement is not a quantum operator. So how when they are doing computation, they actually apply several sequences of operations, and they do measurement only towards the end to see whether they got desired outcomes or not. Okay. Yeah, so it is equivalent of function. So every function, now for so suppose if you are transferring say x to f of x, right? So even in classical computations, this actually boils down to executing some circuit. So you take some input x, and then you need to apply some circuit in classical computers, and then you get some output. So even in quantum also, for every f, you need to compute some equivalent quantum circuit. And then once you apply say quantum input quantum state, you get some output quantum state which acts on this input quantum state. So it is also equivalent to function, right?
Round brackets.
Yeah. So
Elsewhere
here
you haven't used it. Only here you have used.
yeah. So here So here we use ket notation. Yeah, bra notation we can use here. Yeah. So essentially it becomes x. You transpose y. So these two are equivalent. Yeah, so we apply some sequence of operations, and once you do measurement using some basis, you get some outcomes. Hopefully those outcomes are the ones which you expect. Yeah, we need to redo it. So in quantum, although you get outcomes, but sometimes these outcomes are random. So hopefully you get desired outcomes with high probability. So you need to apply operations in such a way that most of the time you get what you expect. Okay. Yeah. So because you apply sequence of operations, right? Say x you start with some initial state x, you apply some u1, okay, and then you got some state, you apply some u2, you got some state, okay, you apply u3, okay, you reached some output, right? So that output is some combination, right? Say ZIs, basic states are ZI. So now, so this is output. Now all these operations, they change these coefficients alpha i's. So when you measure, say, in this standard basis, you should get outcomes because this modulus of alpha I square influence final outcomes. So you should get desired outcomes with high probabilities. Maybe you should get always, say, all zeros. So all zeros means the alpha 0 should be 1. So there could be some other output states. So essentially you need to modify these these coefficients in such a way that it helps in your applications and so on. And also another advantage is, right, like when you apply single, so this is a single quantum operation. When you apply single quantum operations, this is called quantum parallelism. Okay. So when you apply this single quantum operation, which means that there exists only single quantum circuit, you just give one input. That input is essentially this combination, that is single quantum state. And what it does is essentially it acts on all the basis states. So in classical world, you need to actually apply 2 power n times. In classical, you need to execute this operation 2 power n times in classical. But if you apply here in quantum only once this operation, it simultaneously acts on all the basis states. So this is called quantum parallelism. Okay, so U is acting on all the combinations at a time. And then this outcome, this quantum state may not be the one which we want. So you need to probably further modify this output status by applying some other operations. Okay, and we need to make sure that with high probability we get what we want. Okay. Yeah, essentially these operators are linear operators. So if you apply once, it acts on all the basis states. So parallel means simultaneously it is acting on all the basis states. So that is a property of quantum state, right? Quantum state is a superposition. So if you are if you are changing the state of single quantum state, which means that you are also modifying all these superposition coefficients.
Quantum basis state.
Yeah.
So if we apply on the one particular state, which will actually change all the bases.
Yeah. Okay. So this is a quantum parallelism. Because of linearity, we have quantum parallelism, and from there we need to exploit. So depending on what is the problem you have in mind, so you need to find out right operators. Okay. For example, in QKD, like Peter-Shor's algorithm, so they were able to find correct operators which can reduce the complexity. Okay. For example, factoring large integers takes exponential complexity in classical computers, but Peter-Shor showed that it requires only polynomial time complexity using quantum operators. So it depends on the given problem. Okay. So I will now explain simple gates. So there is identity operator. So essentially they translate 0 to 0 and 1 to 1. Okay. And this operator also can be written in matrix form 1001. Okay. Not gate. So if you apply 0, apply x 1. And in matrix form it is 0 1 1 0. Okay. And in matrix form so similar to our classical digital circuit, we have these simple logic gates. Okay. So every quantum circuit can be built using some simple gates like these 1 qubit gates, and there are some 2 qubit gates, and we can build complex quantum circuit to execute quantum algorithms. Okay. There is another gate called Hadamard gate, which is denoted by H. So what it does is essentially translate 0 to plus state and 1 to minus state and plus to 0 state, and similarly minus to 1 state. Okay. And in matrix form, this is the notation. Okay. So from here you can observe that H is its inverse. Okay. Because suppose if you apply 0 as input, then you get plus, and again if you apply plus as input, you get 0. So H inverse is equal to H. So this will play a role in generating entanglements. I will show you how it generates. Okay. Minus means like, okay, we have these complex numbers, right, in the superposition. The angle is like 180 degrees. No, in that superposition, the coefficient of 0 is 0. That's why 0 was not there here. And the beta is actually minus 1. Beta is minus 1 there. And so I will explain just one 2 qubit gate, which is CNI gate. Okay. So what it does, so the circuit is this x1, x2, x2 bar, x1 is 1, x2, x1 is 0. So this is called control bit. This is called target bit. So essentially, suppose if x1 is 1, then you will flip x2, and if x1 is 0, then you will not change this x2. Okay. So if x1 is 0, it remains the same. If x1 is 1, it will flip. Okay. So basically what it does, it is introducing some correlations, some coupling between x1 and x2. So depending on what is the state of x1, we are changing the state of x2. So this idea is used in generating entanglements. This is also one of the entangling gates, which means that it can create entanglements between two different qubits. Okay. How does it, how can we create entanglements? Suppose you start with 0 0, you are applying H gate on the first qubit. Okay. So which means that, so tensor product means that this first gate is acting on the first qubit, second gate is acting on the second qubit. So this changes the state to place 0, because H, when you give input 0, it gives plus state. H is Hadamard gate. Okay. Now if you apply CNI gate, okay, it will, CNI gate means this circuit, then you will get 0 0 plus 1 1 divided by root 2. So which is an entanglement. So this is called Bell state. So in lab, suppose if you start with both horizontal polarization, you can create an entanglement by applying these two operations. Okay. Yes, it can. So place also can be written as superposition of 0 and 1. Yeah, place means like 0 plus 1 divided by root 2. Yeah. Yeah, you can convert, yeah, from one state to another. So here, so here it is not like basis. This here basis is like a qubit. Basis means when you are taking this entire set and then applying some measurement or superposition and so on. And of course, when you by applying H, you can convert input quantum state to different basis states. Okay. Yeah, I have not written here, but it has some matrix representation. I have not written here. Okay. And here we need to convert. We are assuming here x1, x2 belong to 0 and 1, not plus. So here we are assuming that the input state basis is standard basis. Okay.
A universal gate like
Yeah.
can we like express it in terms of XYZ and Hadamard? It's possible, or
Yeah. So ultimately, we want to build any complex quantum circuit using some simple gates. So C0 gate is part of such set. C0 gate, and there is this Hadamard gate, and there is another gate called T gate. So using these three gates, we can approximate any quantum gate, any quantum operator.
no? I was asking like, can you break down C0 into these other gates? That
No, you cannot. Why? Because suppose here, for example, you can, if you are taking any single qubit gates, they change only particular qubit. They will not disturb any introduce or disturb any coupling between qubits. So C0 gate is the only gate which creates some coupling between qubits. So all these gates, they act only in individual gates, in individual qubits. That's why you need this gate as part of universal set. Because if there are some quantum states that have some correlations among qubits, so you can use C0 gates to represent those correlations. Yeah.
-1, right? And that you are writing it as a first column. 0 and the output -1 is in the second row first element. Okay, I'm telling about Y gate.
Okay.
And in Z gate, if it goes by that, then it should be 1 minus 1 0 0, right? How you are writing that?
So this one. So here, like basically, 1 means in vector form 0 1. So if you multiply this matrix, do we get -1? You can try here 0 1. I don't know whether if I made any mistake. 1 0 0 1. So we get 0 0. Yeah, -1. So which is essentially -1. So which is actually -1 state. So this is correct.
No, actually what you are...
There is error here. Yeah. So Y gate is here.
Yeah, Y gate is, you are selling, no, that what is that multiplication? I'm not able to get it.
Yeah. So essentially here, so we need to, for example, -1, 1 -1, they are in this diagonal, right? So when we apply X, they actually make this 1 -1 to zeros, like, right?
No, can I get the mathematical formula from this
Yeah,
notation?
if you multiply, these, for example, these matrices, you will get, this matrix.
No, that's what, how you are ending up there. See, I will start with one.
Yeah, actually I haven't given proof, but you can check this one.
Okay.
So applying Y gate is equivalent to first applying X gate and then applying Z gate. Both are same. Yeah, this is correct.
Now, how you come to that form?
Oh, okay, so I got it from a textbook.
Okay,
Okay,
fine,
so I'm not deriving, but
okay,
yeah.
fine.
So if you apply this matrix, for these inputs, you will get these outputs. Okay, so they are equivalent matrix representations. Okay. Yeah. So here, so place means this one, right? So now we need to expand this. So we need to take product. So it becomes 0 0 divided by root 2 plus 1 0 divided by root 2. Okay, so here we need to convert quantum state to all zeros and ones representation, and then we apply C naught. Okay, so this one remains the same because control bit is 0, so you get 0 0. But this one is 1, so therefore you need to flip the second qubit, so you get 1 1. So now next we will prove an important theorem which is called no cloning theorem. Which essentially says that an unknown quantum state cannot be cloned or copied. Okay. So what we will show that suppose you come up with an operator U such that if you apply, so this is a given input quantum state and there is some dummy state 0, okay, and if you apply U on this, so you get psi psi. and we do not know what is psi. You have received some qubit and you want to create multiple copies. Can I find some operator u such that you can create 2 copies starting from 1 copy? Okay. We will show that such u will not exist. So this is called no cloning theorem. Okay. So this is part of quantum key distribution. Someone is sending quantum keys across fiber optic channel. If there is some eavesdropper, if he doesn't know how those qubits have been prepared, then the eavesdropper will not be able to copy them. Okay. But in classical systems, we have relays, which can actually receive weak signals. They can create multiple copies. They can amplify received signals. But in quantum, we cannot do that. So sometimes this is an advantage. Sometimes this is a drawback when we are building quantum networks. Okay. So I will formally prove this one. Okay. Suppose that if you can find some u, which is if suppose that u is called copy machine, okay, which can actually copy these input quantum states to different quantum multiple copies. Okay. Yeah, u is some operator. Suppose that there is some operator which can create multiple copies of some unknown input state. Okay. So and we will show that such operators cannot exist. Yeah, when I say operator means it is essentially a collection of different gates executed in certain order. Okay. Yeah. Yeah. No, so this is it is a joint state. This is called tensor product. So essentially, this is the first qubit. This is second qubit. Okay, outer product means it is something like this. That is outer product. So now because we assume that copy machine exists, so we must have u00 equal to 00, u10 equal to 11. Okay. So here when I say 00 means it is essentially like 0 and 0. So this is a short notation. Okay. And we have psi to be alpha 0 plus beta 1. And these alphas and betas are unknown, we do not know about them. Okay. And so and since this operator exists, u exists, from the property of copy machine we have this equal to psi. And next what we will show that we will expand this expression and show that such an operator u will not exist. Okay. So essentially u psi 0 equal to alpha 0 plus beta 1, alpha 0 plus beta 1. So we will multiply the terms in these brackets, and after multiplications we get alpha square 0 0 plus alpha beta 0 1 beta alpha 1 0 beta square 1 1. Okay. So I am calling this as 2 and this is 1, and we have also another way we can write. So u psi 0 is essentially u alpha 0 plus beta 1 times 0. So we will expand this expression, which means that alpha 0 0 plus beta 1 0. Okay. And since u is linear, right? So we go to alpha u 0 0 plus beta u 1 0. and from the fact that it's copy machine, so we get alpha 0 0 plus beta 1 1. Okay, because U is copy machine, so it copies the first one to the second qubit, so which is 1 1. Okay, so we have two equations. For the same expression, we get two different expressions. One is this one and another is this one. So now we need to compare these two equations. Now we see that in these equations some terms are missing. 0 1 term and 1 0 term is missing here, and 0 1 and 1 0 term is available, is present here. So now can we find some alpha beta such that they do not coincide? Okay. So and for example, if we take say alpha equal to 1 by root 2 and beta equal to 1 by root 2, these two equations they do not coincide. So which means that U cannot exist. Mm-hmm. Yeah.
It to be a type of copy gate.
Yeah, you are correct. So I will explain. So in this particular case, for 0 1 qubits, CNOT gate is copy machine.
Yeah.
But suppose if you give, okay, so it cannot copy here. See, if C0 is copy machine,
Right.
plus 0 should become plus plus.
Yes.
But that is not correct.
But can't we break it and
Yeah.
into zeros and ones and
Yeah.
then copy it into parts?
Yeah, so it can only copy zeros, every states that is a combination of 0 and 1.
Yeah.
So input state should be orthogonal.
Yes.
So then they can copy. So I will give some remark.
Okay.
That is an excellent point. So there are some conditions under which you can copy certain input states, and those input states should satisfy some properties, which is that all the input states that can be copied should be orthogonal to each other. Then you can come up with a circuit. For example, you can copy plus and minus states because they are orthogonal to each other. You can copy them. Okay, but you cannot copy 0, plus and minus. Why? Because 0 is not orthogonal to plus and minus states. So you cannot find some copy machine which can copy all three of them. But for these two, you can find some circuit.
Okay.
Okay. Mm-hmm. Mm-hmm. Okay. Here. Mm-hmm.
Then we write alpha 0 0, alpha beta 0 1. When these two are combined, like I mean, what we are actually doing? Is it forming an entangled band or?
No, it is essentially saying joint state. So for example, this says that okay, joint state of the state of the first qubit is this one, the state of the second qubit is this one. Now, so which means that now if you multiply this, it says that okay, here it says that the first qubit is in 0 state, the second qubit is in 0 state. Here it is first qubit is in 0 state and second qubit is 1 state. And then we have some coefficient which corresponds to superposition.
So in this way, like we have alpha beta, which is alpha square plus beta square, and it represents some probability of 0.
Yeah,
and
you will get.
So for the two states, then we will get alpha square as the probability that both are in 0, and alpha beta as
Yes.
both in 0 1. So in that case, the 0 1 and 1 0 probability becomes same.
0 1 1 0. Yeah, it can become same. That is not a problem. Yeah.
It should always be same, right?
No, yeah, so in this case they will be same because you are getting 0 and 1 0, by multiplying
Because
different.
alpha and beta are same, so that's why
Yeah,
in
yeah.
this case,
Yeah,
it will
so this
always
is
same.
alpha beta, product of alpha and beta is another complex number. Beta alpha is another complex number. So in this special case they will be same, but in different states they need not be same.
If we have alpha 1 and beta 1 and alpha 2 beta 2, then we can have alpha 1 beta 1 and beta 2 alpha 1. Yes.
So for example, if you are taking two qubit states, if we can write them as product of two individual qubits, then their coefficients should have this property.
Okay.
Then you can write them as separate individual qubits.
So, but this is not this representation. This does not mean entanglement.
No, because you can write them as product of two separate qubits. So there is no correlation among qubits. Okay. Okay. Yeah. Oh, sorry, sir. No, no. Here. Uh, yeah. No, but if it copies, so this is. I am assuming here this is equal to psi. So if copy machine exists, this copies the first qubit to the second position, which means psi. Therefore, we get same coefficients here. Okay. So now, for example, if you give alpha equal to 1 by root 2 and beta equal to 1 by root 2, so these two equations are not the same. So therefore, u cannot exist. Therefore, Therefore, u cannot exist. So if it exists, it should copy all the states, like if our scanning machines, right? If it can copy any document, any PDF if you give it doesn't differentiate what is a text on those documents. Here it is differentiating. For example, there CNI gate can copy 0, 1 states, but it cannot copy plus minus states. Okay, so you cannot find a universal copy machine which can copy all the input states. This is just one counter example. So if you substitute these values in these two equations, they will be different terms. For example, 0, 1 is 1 by 2, but in this case 0, 1 coefficient is 0. Therefore, these two equations are not the same. Yeah. Yeah. But if you want to prove that some property is true, if some property is not correct, you just need to find one counter example. So this counter example is that if I take these values, these two equations are not the same. Therefore, U is not a universal quantum copy machine. There can be specific case, but if copy machine exists, it should copy all the states, not only some specific states. Okay. So yeah, only, and those states should be orthogonal to each other. Then you can come up with a copy circuit. Okay, so this I will give one remark, which is what pointed out by some of the members. So this is one of the important properties of quantum mechanics, no cloning theorem, which means that if you don't know about some states, you cannot copy them. So there can exist copy machine that copies states that are orthogonal to each other. Okay. So for example, for 0, 1, you can find CNI gate. Okay, and similarly you can find for plus minus, because these two are orthogonal. Okay, but if you cannot have a copy machine for this set. Okay, so you can find for this one, but not for this one. You can prove this, okay, by again assuming that these all the states that are that can be copied are orthogonal to each other. You can show that U can exist by repeating these steps. Okay.
According to the definition of no cloning theorem, it says an unknown state, quantum state, cannot be cloned.
Yeah.
So this is
So
not an
here,
exception according to that definition.
yeah. So here, you should at least know the basis. Suppose sender is there. You know that sender is going to send only in Hadamard basis, either plus or minus.
Yeah.
Then you can create a copy circuit, copy machine, because
Yeah.
you can come up with a circuit which can copy plus or minus. You need to know the basis, not the exact state. Suppose if you know that the sender uses only standard basis, either 0 or 1, then you can copy. Not superpositions also, just 0 or 1 or plus or minus, because the set has to be orthogonal.
This is not an exception to the no cloning theorem, right?
Yeah, so yeah, it is not, no cloning theorem is what I have proved.
Yeah. Okay.
But this is a remark. Under some situations, you can come up with a copy machine.
Only talking about the basis, it means like bases are collapse states, which are actually a classical state. So we're not actually copying a quantum state, we're actually copying a classical state.
No, like plus is not a classical state, right?
So yeah, if we are talking about plus in the Hadamard basis, so
yeah. So it is similar to basis. So plus is, some kind of like 0 representation, some kind of 1. So you need to know the basis. If you know the basis, then you can create a copy machine. But the data that they send should be only plus and minus, not superpositions of plus and minus. So this is a particular situation.
So another doubt, like you said, for some cases alpha and beta can exist to satisfy the two equations. But
yeah.
Like the only case we could found was alpha and beta equals 0, which is not a machine.
Okay.
So like.
So like I've given these examples, right?
That is just something classically copied. But it's not a machine for copying a quantum state. That is what I'm saying.
Okay, so next we will go to quantum parallelism. Yeah. Yeah. Yeah.
So both alpha and beta should be 0. That will be a contradiction.
Yes.
Therefore, we can use method of contradiction to prove that result.
Yeah. So that actually covers all states.
Yeah. Without taking that counter example, then it will be more clear, I think.
Okay.
Comparing 1 and 2, we will get alpha and beta should be 0. That will contradict our assumption that we are taking any arbitrary ket psi, I think. So we can assume that it is non-zero because we are assuming for all vectors.
Yes, that is a correct explanation. So here I just gave a specific example.
When we give example, we are not getting a contradiction. So I think you can use method of contradiction.
So basically you need to compare the coefficients of these two equations and try to find whether we can find some alpha or beta satisfying these equations. And those comparisons will give us alpha equal to beta equal to 0. But now if you take alpha equal to 1 by root 2, beta equal to 1 by root 2, these two equations will not coincide, therefore counter example. Alpha 1, no, I think it may not work. Alpha 1,
from that
okay.
we will get alpha and beta must be 0.
Yeah, if it is copying all the states. Okay. So we can proceed. If you have someone has still doubts, we can discuss offline. Okay. So for any function that we want to compute, so we need to compute come up with a UF which executes the same function F. UF is an equivalent quantum circuit. So for this UF, if we give as input X and Y, okay, then this output is, okay. So generally we choose generally Y equal 0. Okay. So which means that this will have, so this term will become X and F of X. Okay. Yeah, it is operating both X and Y. Basically what it does, it computes F of X and then applies. So here X and Y are assumed to be zeros and ones. Okay. And it will apply XOR operation between Y and F of X. So basically this circuit becomes, reversible gate. So from here you can again go back to this input state. Suppose if you apply F of UF again here, you will go back to this input state. Okay. So this is a reversible quantum operation. Okay. So now I assume that psi is equal to some superposition of input basis states. Then UF psi 0 essentially becomes summation over I AI UF xi 0, which is equal to summation over I AI xi. Okay. So because every quantum state is a superposition of basis states. So from using this operation UF, this UF acts simultaneously on all the basis states Xi's. So therefore you can get this F of Xi value in this basis state. So you have now full information about all the F of Xi values. So with just one operations, this superposition contains all F of Xi values. So now we need to further modify these output state to get desired results. Okay. So for example, if you compute what is the Xi value that minimizes function F, so probably you need to apply some extra gates so that when you measure final output, with high probability we can compute Xi that minimizes F value. Okay. So that is this is called quantum parallelism. Okay. Yeah, it's the same actually. So this is equivalent to psi 0. So this product is same as psi 0 in a single bracket. Okay, for example, so this is same as psi 0. Okay. So there is one. Yeah.
But then if you just treat it as an identity function, wouldn't it be like a copy circuit?
Identity. Identity operator. No, identity operator is just like.
No, like you consider that f to be like an identity function. So what you would get is like x and x.
No.
Will it not be a copy circuit?
No, you need to expand that.
Okay.
So it will not. You can try. See, identity. What does identity operator do? Right, psi 0 should be mapped to psi 0, not psi psi. So this is the input state for the identity operator, which means that it takes this input state, it gives the same psi 0. It will not give psi psi.
So over here, right, this particular quantum parallelism, this UF that takes x comma y and gives you x comma y XOR with f of x.
So here I am assuming that this x is in basis form.
Okay.
So either it takes only zeros and ones. Now general quantum state is a superposition of such x's.
Right.
Okay. So here it takes only zeros and one, not superpositions. But in general form it takes superpositions.
Oh, okay. So no, I did not understand. So over here, you're saying that x should be either 0 or 1.
Yeah, it's a combination of only basis states.
It's a combination of basis states.
Okay, when I say combination, mean it's not like superposition or something like all 0, 0, 1, 1, 0 like that.
Okay.
Not like here.
Okay, and like let's say if you have a superposition of those, then this quantum parallelism will not work, or?
No, it will work. Why? All the quantum operators are linear.
Right.
So this is linear. So we are going from here to here because this UF is linear. And this psi has this structure, this form. So psi has this superposition, and then we expand that expression. And if you apply UF, because of linearity, we can get this expression.
Okay. Okay. Maybe it's not clear, but I'll talk to you later. Yeah.
So the identity map should go to 0, 0 plus 1, 1. That's what I'm saying. Because if identity x on 0, it gives you 0, but if identity work x on 1, it gets 1. So the state will be 0, 0 plus 1, 1. So you have wrote that psi 0 goes to psi 0, which is, I think, it's wrong according to my understanding.
Okay, you are saying this f is like I.
When he said identity will be copying, you said that it will psi of 0 will go to psi of 0. I am saying it's not go to psi of 0. If psi is 0 plus 1 and by root 2, it will go to 0, 0 plus 1, 1 divided by root 2.
No, but according to the definition of identity operator, it should map the same input to the same, because this operator acts completely on all these bits, qubits. Right? Identity operator means we should get the same input as output. So it should be psi 0. Right?
So here you have written UFX match from x.
See,
x,
so UF is some circuit. I am not explaining how you can find circuit UF. So you have to find a way such that when you give UF on this circuit, it gives outputs in this way. I am not telling you how to compute that UF. So we have to assume that there exists some circuit UF that gives this output. Okay.
Okay, so one more question. So if we have function, like generally when you speak of function, there is no constraints of like about being a unitary or anything. It can be any function. But right now we are telling that for every function there exists a UF. So, but you have a constraint that its determinant of it need to be unitary.
Yeah, that is all, because all quantum operators must be unitary.
Don't you think like all functions can't be mapped to unitary functions?
Yes. So in classical computations, some operators are not unitary. So what they do, they actually add extra gates, because some classical circuits are not reversible. So they add extra inputs, extra gates, and then they make it reversible. And then we can reverse that, we can make classical circuit unitary. Okay. I will give one example. Not UF is unitary. Yeah, that's all. Say suppose you take AND gate, right? Say you get x1, x2. So if you have one output x1, x2, this is not reversible. So you will not have a quantum operator executing this. But if you have this one, then this is reversible. So here what we are doing, we are using some extra output bit that keeps x1 value. So using this, you can actually go, okay, so this one is product. So you can go back from here to here. Okay. So some classical circuits are not, yeah. So we need to convert classical circuit to reversible circuits first, and from there you can get reversible unitary operators UFs. Okay. So that is how we can show that quantum computation is as good as classical computation, because all quantum computations are reversible. If there exists some classical computation that is not reversible, then how will you prove that quantum computation is as good as classical computation, right? So you still need to show that you can, first you need to translate irreversible classical circuit to reversible classical circuit, and then you need to come up with UF and show that UF also takes similar complexity. Mm-hmm. Yeah, but you can prove that, I mean, they have shown that all classical circuits can be reversed by using more and more gates, more storage bits and so on. So you basically need to use extra bits, extra memories and so on. You can always come up with some classical circuit, reversible classical circuit for any given input classical circuit. Okay, you will just use some polynomial number of extra gates. So polynomial is always manageable. So we do not want exponential complexity. Okay. Mm-hmm.
Here, like you said, that x is a basis of 0 and 1.
Yeah.
And there, then you can consider that this psi, which is a combination of some states, xi's.
Yeah.
So in that case, can we have a phi function which we can consider y as some kind of phi, where we have a combination of yi's with like sigma bi yi, and then we can apply this unitary operator UF. Can we do that also?
Sorry, I didn't get your question.
So here we have a psi equal to ai xi, summation of that. We can have something other phi, suppose, that which is a combination of bi into yi.
Okay. Yi is another basis?
Yes. Okay. So in the, then can we apply this unitary operator, and but here you have like considered 0, like in that case we will get a yi XOR with fxi.
No, actually we assume that the input basis is always standard basis. So suppose if you start with some other basis, you need to translate that into standard basis.
So but like x and y are a standard basis, right?
Yeah, but if you are say considering some plus minus state or something, so here assumption is that f takes only like 0, 1 bits and so on. Okay. So maybe we can discuss offline. Okay. Mm-hmm.
Z is a function of x also.
Mm-hmm. Okay.
Two operations.
Yeah. So if
Z is g of x.
Yeah. Okay. Yeah. Okay. So now, like in this case, so f is so you are considering UF. You are saying xz. Is it like this? Okay. Yeah. So this is some dummy variable. So you can choose here y equals 0. if you choose y equal 0, you get just f of x. But if you choose something else, say z is equal g of x, then here instead of f of x you get something like g of x plus f of x, g of x or f of x. So this is some other function. Yeah. U is x comma y comma z. Okay. So essentially we are extending more bits. Yeah, more bits. Yeah. Yeah, you can also do that. Yeah, you can also do. So these are all simplest cases, simple cases. Okay. So we have something called Wallace-Hadamard transformation. So this transformation essentially applies Hadamard gate on each of the qubits. Okay. So you can show that if you take 0 0, you can get superposition with all coefficients being equal. Okay. So here all the coefficients are 1 by root 2 power n. Okay. So this is used very often in quantum computation. So if you start with the initial 0 state, how will you generate the superposition that you want? So you start with this, and now this has some superposition where all the coefficients are equal, and from there you need to apply extra operations to get desired superposition. So I will explain one case, how where they were able to show that quantum computation is better than classical computation. Here, so coefficient is this one, 1 by root power 2 power n. All coefficients are real numbers. Yeah, like this. Yes, on all qubits. Number of input qubits. Yeah. Yeah, it will have starting from all zeros to all ones. With so here xi belong to this one. It will contain all of them, and the coefficients for all these basis states is just 1 by root square root of 2 power n. So we can get started on our topic. So we will first discuss what are some challenges in quantum communications. So similar to our current internet, once quantum computers are developed, we need them to talk to each other so that we can use them for different applications, right? And so one way is to directly transmit qubits across communication channels from source to destination. Most widely used channel is fiber optic channels. Okay. And qubits are photons. Okay. So why do we want to use fiber optic channels and photons? Because we already have networking infrastructure in our current internet. So we would like to use the same network infrastructure by using two communication channels, one for classical internet and one for quantum internet within the same fiber optic cables and so on. So in that way we can reduce cost. And the second is that photons are the best qubits that have good communication properties over all other qubits. For examples, there are some qubits that are very good for computation, and then there are qubits that are good for communication. So fiber optic photons are good for communication. Okay. For example, if you have two quantum computers, okay, so we will use some different qubits for computation. So these are used for computation. Okay, and then we have some qubits which are used for communication. Okay, so we need to allot certain number of qubits for computation and certain number of qubits for communication. And the communication channel generally is fiber optic channel, or you can use free space. So but in free space there is a lot of noise. Okay. So once they compute results using computation qubits, they have to transfer these results using these communication qubits to other end. Okay. Now we can transfer these results by directly sending photons on this fiber optic channel. However, there is a significant loss in photons when we are transmitting them. So loss of photons is significant when we are sending even on fiber optic channel. So this probability of success is proportional to like e power minus alpha L, e power minus alpha L, where alpha is attenuation coefficient. So, so if you are sending due to attenuation in within the fiber optic channel, this probability of sending photons to the receiver decreases with the length of the fiber optic channel exponentially. So L is the length. So L is the length. Okay, and in practice this L should be less than 100 kilometers. So our practical fiber optic channels support us for quantum communications when the distance is less than 100 kilometers. Okay, and if you have the distance to be more than 100 kilometers between sender and receiver, then we have to use some other quantum mechanical device and quantum mechanical properties. Okay, and so this is one challenge. Another challenge is no cloning theorem. Okay, which means that if you have say sender and receiver B, and in between we can use some repeaters or relays. Okay. So in our classical communications, we use some intermediate devices which actually can receive some weakened signal. They can apply some error correction, they can amplify them, they can create multiple copies and then retransmit them to intended receivers. But according to no cloning theorem, as we just seen, if intermediate device doesn't know what has been received, then it cannot copy them and amplify them. So that is also another challenge. So in quantum cryptography, no cloning theorem is an advantage, but in quantum communication it is a disadvantage. So we need to overcome these two challenges if we want to use quantum communication. Okay, and
classical communications where you're communicating
yeah,
this.
yeah. So but they can
Use these repeaters to.
yeah, they can amplify them.
Okay.
Okay, but here we cannot amplify them. Okay, but so now there is, to overcome these two challenges, we have some quantum mechanical properties which we can exploit and use them for quantum communication. So that is that principle is called quantum teleportation. So basically, suppose we have two users, okay, A and B. Sorry.
Classical methods for communicating this information.
Yeah. So in quantum, so quantum will not actually increase the speed of communication. So we are, even in classical communication, we have already reached Shannon limit. So quantum will be used for different applications like quantum computation. So you will get better computational power. Quantum sensing. So you will have, because quantum atoms are very delicate. So even if there is small change in the system, in the environment, they can easily identify them. So quantum sensing, clock synchronized, cryptography. So there are different applications of quantum, not communication. So here we are not trying to increase the speed of speed of communications compared to classical communication.
So in like those application, you're saying like the normal classical way of communicating will not work.
Yeah. So for example, classical cryptography. If someone comes with quantum computers, they will not be secure.
Okay.
And also supercomputers. For example, there are some companies, some experiments are claiming results, algorithms that can be solved using in billion years using supercomputers can be solved in just 10 minutes using quantum computers.
Okay.
So quantum technology has some different applications, and once these systems are in practice, people will come up with probably different applications.
And like quantum key distribution, that is using quantum communication, is it? Or
yes, for example, quantum key distribution involves sending qubits from source to destination.
I see. Okay, okay.
For that, suppose if the distance is less than 100 kilometers, okay, the direct transmission is possible. But if the distance is more than 100 kilometers, then direct transmission will not be possible. Suppose if we have companies, international companies, say like Cisco, if they have branches in Bangalore, they have branches in California. If they want to exchange some files, and which needs to be secure, then they have to use probably quantum cryptography. Then how do we send quantum bits between from India to US? Direct transmission is not possible. And hopefully using satellites in future, once quantum internet is developed, we can do that.
Okay.
Not going to increase the speed, but can it increase the bandwidth, because we are actually sending the states? So in that way, like somehow can we because like the example you showed out, 200 2 raised to 300 is more than the number of atoms in universe. So in that way, can we increase the bandwidth of the quantum communication?
Okay, so I am not sure about that. So of course we can also, using quantum, we can also send classical bits. Okay, so but that will not, I do not think it will increase the speed. Yeah. So maybe in between quantum parallelism, I don't know whether there are some theories showing that it can increase the speed as well. But the purpose in general is different. So now we have, say, two users A and B. We have some entanglement psi which is said between A and B, such that one qubit of psi is here. Okay, another qubit is here. Okay, this is a 2 qubit entanglement. Psi is a 2 qubit entanglement, so it has 2 qubits. So one qubit is available at A, another qubit is available at B. and suppose that you have some data qubit V. Okay. Then using this entanglement, we can transfer this data qubit to B. And here the distance doesn't matter as long as they have a pre-existing entanglement. We don't know how it has been established. Suppose there is some entanglement already available to us, then you can send V to B from A to B. Okay. For example, you could create this entanglement using satellites. For example, China has shown that you can do this even when the distance between A and B is 200 kilometers. If you have entanglement, then you can transfer data to anywhere. Okay. So entanglement will have the same role as wireless channel in wireless communications. So if you have entanglement, then that is a transmission, like it's like a transmission medium. Okay. Then you can transfer to anyone. Okay. So that is the reason in quantum networking we focus a lot on how to distribute these type of entanglements between different users who are connected to a quantum network. For example, A could be a quantum computer which is executing some algorithm, B could be another quantum computer executing some algorithm. If then A can send its results to B, they can combine them and come to some conclusion. Okay. Or they can do some quantum cryptography. Okay, this could be some location of a bank, this could be another location of a bank, they are sending some secret information, they can encode using quantum bits and so on. Okay. So now I will explain how this teleportation mechanism works. Okay. Yes. So if they have entanglement, you can send qubits from one place to another. Also here note that there is no actual transmission in this mechanism. You will see there is not actual transmission. In fact, you need classical internet. You will send some classical bits from A to B during this teleportation mechanism. So you will not transfer any quantum bits. So at the end of this algorithm, you will see that V will appear here and it will disappear here. So basically both of them apply some operations locally, and the final outcome will be that V will be here and it will disappear from here. And during this mechanism, this psi will be consumed, this entanglement will be used in this process and it will be destroyed. Okay. So we are considering this entanglement. So this is also an entanglement, and in this case I am using subscripts to indicate that this qubit is located at A and this qubit is located at B. So this is the first qubit, this is the second qubit. Okay. And the data qubit has this superposition. Okay. So this is a superposition of the data qubit V. Okay. So now we will consider, so A has two qubits, right? One is V and then it has the first qubit of this entanglement. So what it does now, it will measure the joint state of V and the first qubit of entanglement at its location. Okay. So the joint state of V and So this is essentially the joint state. So this is the V is this expression and psi minus AB is this expression. Now we multiply all these terms. Okay. So and if we multiply these, we will get this expression. Okay. So basically this is expansion of this term. Now, so now the first 2 qubits will be measured using the Bell basis. So I will explain what is Bell basis. So user A, which has V and the first qubit of entanglement. So these 2 qubits, the qubits that are in the first 2 positions, will be measured using some basis. Okay. And we consider the following Bell basis. So so as you can see that, so these are also called Bell states. So all these 4 states are entanglements. Okay, and they are all orthogonal to each other. Okay, so now you can come up with some measurement device, 2 devices essentially. Their joint state can orient in any direction. Okay, if you have 4 detectors, you can detect the, using you can detect these type of entanglements. Okay, so the next step is to measure the first 2 qubits. So they are same, like these 0V only. Yeah, they are not the same. So essentially 0V means that it is a data, it is a part of data qubit V, and 0A means that it is a part of the qubit of entanglement that is located at A. So we have different subscripts. Okay.
Same if like A is different, V is from data bit, and
yeah, when you are multiplying these things, right? So this alpha, okay, so alpha, now this is one term, now you are multiplying 2 terms, so you will get 2 terms where alpha is present, and similarly beta. So it is regular multiplication of terms.
so why we don't have any like alpha or beta for A and AB?
Okay, maybe did I do any mistake? So alpha, so there are no, there is no alpha beta, right? See, alpha, you need to multiply this term with these 2 terms.
Yes.
Next is this term with these 2 terms. You will not get alpha beta or beta alpha.
No, I mean that those 2 terms, like it seems, which are entangled. Um, so we don't have any coefficient related to them with
So
the
this
AB.
okay, this coefficient is 1 by root 2.
Okay, same coefficient is
Yeah, so 1 by root is also real number, scalar. Yeah.
Okay.
So 1 by root is a coefficient for these two basis states. Mm-hmm. Mm-hmm. Yeah, here. Yes, joint state. Yeah, not individual, joint, like two particles together is this. You cannot talk about them individually because they are coupled. So their joint state is this.
So I am not able to understand. In that diagram, you said like one
Yeah.
supercomputer has A and the other one has B.
Yeah.
So what is A and B in this equation, or how does it show?
So they can have two qubits, but they could be located in different locations. In labs, they can prepare such states.
Okay.
Okay. Suppose if first qubit, if I call it as psi minus A and psi minus B as a second qubit, they could be located in different locations.
Okay.
But their joint state can be this.
Okay. Okay.
So
and
I will explain briefly how they prepare these type of states in labs.
Okay, that is fine.
Okay.
But then you're saying you're applying these operations, right? Like you're doing this V into this joint state.
Yeah.
What does that mean?
So it has one V data qubit.
Right.
And it has psi minus A, which is coupled to this guy.
Right.
So these two qubits are available at A.
Right.
So now it can apply this A can apply some operations on these two qubits.
Okay.
Because they are available at A.
Right, but A, the qubit with A, that is in this state phi A, right?
Minus, yeah.
But over here you're applying psi AB, which is what I did not understand.
Okay, so I'm calling this entire joint state as psi minus AB. Okay.
Okay.
So now this can be a collection of two qubits. Those qubits can be like this psi minus A and psi minus. So it is not like product form.
Okay, so whatever this operation is applied on this A, that will actually affect this psi AB wave function.
So you will see that.
Okay.
Okay. So if you change this guy, you will change to this guy. So that is how V appears here.
I see. Okay.
So what happens is that these alphas and betas which were there at V, they move to this qubit.
Okay.
And then you will get these coefficients for superposition at B.
Okay.
Okay.
A.
Yes.
Right. So the Bell basis at B will be different.
Yes, if we apply some operations at B, it will be different. But at B, there is only one qubit.
Oh.
At B, there are no two qubits because Bell basis means we need two qubits. So these are two qubit states. If you have another qubit, probably B can apply again. So suppose if you have another network, say there is another node C. If you have another entanglement between this guy, okay, now B will have two qubits, so it can apply Bell basis again. So I will that is what quantum network is actually. So all these intermediate devices, they need to do some teleportation to go from one end to another end. So these are all very good questions. So A has two qubits, V and the first qubit of entanglement, and using those two qubits, we will construct these bases, these Bell bases. and from Bell basis, so you have these expressions, right? You can write from Bell basis, you can show that 0V and 0A can be written as phi plus VA plus phi minus VA square root T, and 1V and 1A and 0V 1A equal to psi plus VA plus and 1V 0A equal to psi plus VA psi minus VA. Okay. So why I need to write these expressions? Because in this joint form we have these terms 0V 0A 1V 0A and these terms 0V 1A. So we need to replace the first two terms, first two qubits using Bell base terms. So now we will substitute these formulas into that expression. Okay. So if we substitute that, so by substituting the above expressions, so this joint state becomes okay. So basically I just substitute these into that equations. So if you simplify them, you will get this expression. Okay. So now you observe that these alphas and betas, now they are appearing at B. You know, the basis states 1B and 0B has alpha beta as coefficients now. Okay. So now if you measure the first two qubits which are contained in these basis states using the Bell basis, so this is Bell basis measurement. So that contains all these four different states: phi plus VA, phi minus VA, psi plus VA, and psi minus VA. So these are four different basis states. So you can use the Bell state devices that I explained earlier, beam splitters and those things. You need to use multiple devices. So in labs they can do it. So you can do measurements using these four basis states. They are all orthogonal to each other. Okay, for 2 qubit systems. Then you will get some measurement outcomes. Okay. So can you guess what will be outcomes if you measure this state using this Bell basis? So basically you need to measure only the first 2 qubits, and you are not measuring the third qubit. That will remain the same. Only the first 2 qubits will be modified. Yeah, one of these 4 bases, but the other guy is not changing, so you will also get other states term. So essentially, yeah. So you will get this one and these bracket terms. So you will get 4 outcomes, which corresponds to each of these 4 terms. Okay, so you will get, for example, 5 plus VA and alpha 1B minus beta 0B. So the probability is, so here the coefficient is off, so you need to take square of it with probability 1 by 4. Okay, and so here you remember that this the entanglement psi minus AB, it has disappeared now. So now the first qubits, 2 qubits that are available at A, they are coupled in this way, and then the qubit at B, it becomes separate, independent. Okay, and similarly you get alpha 1B plus beta 0B with probability 1 by 4 and psi plus A minus alpha 0B plus beta 1B with probability. Okay. So now we need to convert these states into our initial state V. So our initial state was V equal to alpha 0V plus beta 1V. Okay. So we need to now convert this into alpha 0B plus beta 1B. Okay. So these subscript are just essentially to indicate that they are available at these positions, but they all correspond to say horizontal polarization and vertical polarization and so on. Okay. So any ideas how we can convert this into alpha 0B plus beta 1B? So how do we convert this into this state? Yeah, those things. So now we need to, so depending on what is the state of first 2 qubits, suppose if the first 2 qubits is 5 place, we will apply some corrections at B, different corrections. If it is 5 minus, we will apply different corrections. Psi place, we will apply different corrections. So this information, because these qubits, these quantum states, they are at A. So now A has to send this signal, this information to B to indicate what is its state. And based on A's state, B will make some corrections. Okay.
So what will A send to B?
So A will send to B what to indicate what is its state, what is the state of the 2 qubits that it has.
Okay.
So if it is 5 plus, so you will make some corrections. If it is 5 minus, B has to make some other corrections.
I see.
That's why we need classical internet in quantum, because this control information has to be transferred on classical internet.
Okay. And what will like B measure?
Sorry, B
will also perform some measurement and then apply the
B will not do measurement. It will only apply some gates. B measurement is not a gate. So B will apply some NOT gate, Y gate, X gates to make sure that its qubit is like this.
Okay.
Okay. So I will give some table. So that will tell you what corrections to apply at B. So this is the table. So Bell state of VA at A. So this is the joint state of V and E, A after qubit of A after corrections, after measurement and all. So we have psi minus, psi plus, phi minus and phi plus. Okay. And classical bits sent by A. So this is 1 1 0 1 1 0 0 0. And now the next is whether B applies X gate or Z X at B. Okay. So this is N N and Y Y N Y Y. Okay. So here N means no and Y means yes. So depending on what is the joint state of the qubits available at A, so we will have these 4 different combinations after measurement. So A will now send classical bits 1 1. So for example, in this case it will send 1 1. It means that X and Z should not be applied at B. So B will not do any operation. But if it is this case, it will apply Z gate on its qubit, and similarly in other cases. So at the end of these operations, we will see that alpha 0 B, beta 1 B is the qubit at B. So here there is no transmission of qubits, it is only transmission of these control information on classical internet. That is why classical and quantum, they will work together. We will not remove classical internet and just use quantum internet once they come into practice. Yeah, so it need not measure. I will explain experiment how they do it. So they can place some photon detectors and they will click only when their joint state is like psi minus. They do not do any measurement. So they can place devices. I don't know how they do it in photonics people, but it seems they can detect using some devices whether the joint state is psi minus or psi plus or phi minus or phi plus. Okay. So this is the most important operation of of quantum technology. Even in quantum computation, we will see like distributed quantum computation. Okay. There also we need to teleport important results. Okay. So after doing a lot of executions, quantum operations, you get final partial results. Then you need to do teleportation, because with teleportation you can send results with with high probability. Okay. Because there is no actual transmission here. So now I will explain what was the experiment. So there is a professor in Austria. I forgot his name. So he did this experiment, and he got Nobel Prize for this experiment. How do they do this experiment? So suppose that this is Alice qubit. Alice, okay. A means Alice, okay. B means Bob. Alice is data qubit. like V. Okay, we have some entanglement source. Okay, and these two will be transferred to beam splitter. Okay. So here these are coupled, so entangled photons. These are two entangled photons. So how do they generate the entangled photons? So if you excite a photon, it breaks into two lower energy okay, and once these two okay, this entire setup is called Bell state measurement. Okay, so and they detect only these detectors detect psi minus state in this case. Okay, so this is data qubit V, and in this entanglement source they prepare two entangled photons. They transfer one photon towards this device, and they also transfer this this data qubit also towards beam splitter. They meet at this beam splitter, they go through some interference, okay, and then in some cases their joint state will become psi minus. Whenever their joint state becomes psi minus, then these detectors they will click, means their properties change, and then they will give a hint that okay, entanglement, the joint state is actually the required entanglement psi minus. And once they get the hint, they have to report this to this Bob, saying that joint state is psi minus. So it will actually send 0, 0, 1, combinations of 0 and 1. For example, in this case, whenever they click, they will send 1, 1, which means that the Bob now knows that Bob now knows that the state of this photon is actual data qubit V. Okay, so once once this setup gives a classical information towards Bob. Okay, and this experiment succeeds only with has succeeded only with probability 1/4. So this was initial experiment where it was shown teleportation for the first time in this experiment. Okay, when was it shown? Let me see if I have written. Okay. So yeah, it was shown in 90s or something. So this experiment was successful with 1/4, and later they were also able to detect even psi plus. So using some other set of detectors, which can also detect psi plus, and then the experiment was successful with probability 1/4. Okay, sorry, 1/2, 1/4 plus 1/4, 1/2. Okay, so here there are several randomness. Okay, one is that these two photons, when they meet this device, they should appear at the same time, because they need to meet each other. So they should appear at the same time. And the another thing is that these photons, they could be lost when they are sending across these fiber optic channels. So there are several noise and random events in this process. So the success rate is very small when we are doing this Bell state measurement. So in general like 10 power minus 3 or something, you need to make like hundreds of attempts to get just one success. So why? Because each of these outcomes appear with probability 1 by 4 as I was explaining here. So the joint state of the first 2 qubits here will be one of these cases with probability 1 by 4. Now psi minus, it will be equal to psi minus only with probability 1 by 4, and during that time only we can detect. Because in other cases we cannot detect them. It seems there are some practical constraints. So for example, they could not place like 8 detectors in single, I don't know, in some area and detect all these cases. It seems there are some practical challenges. They can only detect at most up to 1 by 2 probability. They can experimental challenge. Okay. And so so even in this case, when you try to create entanglement, this entanglement also could be noisy. So it may not be having actual properties. So for example, this need not be equal to psi minus. This could become psi plus. So this could be some noise operation. Okay. So there are several practical challenges. Okay. So this is a key idea. Now we will see how to create entanglements between remote nodes. Okay. Mm-hmm. Mm-hmm.
Now the total system is that B and A are now entangled and B is I'm slightly confused there.
Yeah, so after executing all these operations which I explained, B becomes like a separate qubit which is independent of other 2 qubits. Okay. Other 2 qubits will be coupled.
Other two are entangled to each other,
and then the B's qubit will become data qubit that we wanted to send.
Okay, but are A and B entangled?
Not A and B. No. After at the end of this process, A and B are not entangled anymore.
Okay, I mean, I think we just change the basis in the mathematics.
Not the basis. We basically change the properties of quantum states. Okay. So here, for example, we did not violate any no cloning theorem. So V which was present at A, it disappeared and it became like one of these 5 place, 5 minus, 5 place. And psi minus, which was available in the beginning, it also disappeared. There is no cloning. There is no cloning. So we were getting new states at the end of this operation. Okay. Now I will explain how we can create entanglements in quantum networks between different nodes. So now I explain. So that is teleportation. Okay. Okay. So suppose there are 2 nodes A and B. Okay. So we want to create entanglement between them. So they are not in single location, they are in different locations. Maybe they are separated by 30 kilometers, 40 kilometers. Now how do we create entanglement between these guys? So we want to have some qubit here, some qubit here, and we want to couple them using an entanglement. If they are in single location, maybe there are some ways to create entanglement. But if they are in different locations, how do we create entanglement? Okay. So this is a simple quantum network. This is a single one-hop network. Okay. How do they do it? So we have, so just current experiment only. We have two nodes A and B. Okay. And they have some qubit. Okay. So this is called some memory qubit or matter qubit. Okay. And this is also there is also another memory qubit. Okay. So in practice, people use different qubits, different atoms, different particles for these things. And so some of these memory qubits can be used for storage, some of them can be used for communication and so on. Okay. So what do? They excite this memory qubit. So it splits into two qubits such that, okay, so this breaks into two qubits, one qubit, okay. So one qubit is photon, another qubit is still memory qubit. Memory qubit sometimes they also call matter qubit. So it splits into two qubits when you excite it. Okay, and similarly here you excite this qubit, then it splits into these two qubits. So this is photon and this is memory qubit. And these two qubits, so they are like some team, okay, some group, and these two qubits, they are actually entangled with each other. Okay, so these are entangled qubits. Okay, and then they transfer these photons. Okay, so that it's better if I use photon this side. So photon is here, memory qubit here. Okay, so this is one photon and this is one photon. So now you can transfer these to some beam splitter. Okay, so they meet here, and then they will go through some interference, and then their giant state will be detected. Okay, so essentially detector 1, detector 2. So we do some Bell state measurement here. Okay, so can you explain how we can create entanglement between, say, this memory qubit and this memory qubit? Can you explain? So we need to use teleportation here. How will you create entanglement, say, between this guy and this guy? Any ideas?
Right, like after these two protons interfere, right, you measure, you get one of these four states, and then depending on that you apply the operator on these two memory qubits, and they will end up in same state.
Yeah.
Is that the thing?
So essentially we need to teleport. So this is the entanglement here. So psi minus is essentially this guy. This is the entanglement. And this photon is like data qubit. We need to teleport this photon state to this memory qubit.
Right.
Since these two qubits were already coupled, so once you teleport this guy to here, then this memory qubit and this memory qubit will be entangled. Okay, so this photon, this is like data qubit. We need to teleport the state of this photon, and this is like psi minus in that teleportation experiment. Okay, and we are measuring the joint state of this data qubit and this qubit of this entanglement using Bell state, and whenever their joint state becomes certain value, we are applying some corrections at this guy, then the state of this photon transfers to this memory qubit, and then what do we get? These two, so these two, like, they are entangled. So we get one final entanglement between these two. Okay.
I have a doubt. Initially, when you said physically transferring this qubits, like for example, photons, there is some loss, right? So that will you not run into same problem?
Yes,
over
we
here?
will get into same problems. So here, so we assume that the distance is sufficiently small such that you create entanglement with high probability. So maybe this distance is like 15 kilometers or something. They are not in single location. So the length between say A and B could be around 25 kilometers or something.
Okay.
Then using this approach, you can create entanglement between them with high probability.
Okay. Oh, and like you can have multiple such, like if you want to communicate to long distance,
yeah,
you'll have multiple nodes in between.
Yeah.
And they can act like that repeater or something.
So this process is called entanglement swapping, because we have two entanglements, one here, one into here. We are combining these entanglements and creating one final entanglement. Okay. So now, so this is essentially entanglement swapping. So now if you take a line network, simple line network. Okay. So we have different nodes, A, repeater R1, R2, and say B. So these, so we assume that these distances between neighbor nodes, they are sufficiently small, maybe 20 kilometers, 40 kilometers, 30 kilometers, and we create entanglements between neighboring nodes using that experiment. So these are called primary entanglement. Okay. So across every link we create such primary entanglements, and then these repeater nodes, they apply that entanglement swapping. Okay, suppose you create entanglement between this qubit and this qubit, this qubit and this qubit, this qubit and this qubit. So now this node can apply Bell state measurement on these two qubits to perform entanglement swapping, which leads to entanglement between this guy. Now this can apply entanglement swapping between these two qubits, and then it can lead to this entanglement. Okay. So all these entanglement swapping operations they are successful only with some probabilities. So this is how we can create entanglements between any 10 nodes using repeaters that apply entanglement swapping operations. Okay. So as I said, like if you take satellites, so how satellites can help us, you have like two ground stations, right, A and B, right. So they will have some antennas which can receive and transfer signals, and you have some satellites with certain distance. So they have three different layers: LEO, GEO, and MEO. So the first layer is like 2000 kilometers. So LEO stations is 2000, some other 2000 to I don't know, roughly around 20,000 or something, MEO, and some other range is GEO. So up to 500 kilometers we have our regular environment. Okay. So up to 500 kilometers. So during this region, the probability of sending successfully photons actually again decreases exponentially with length. But then during this remaining region, like up to 1500 kilometers, it decreases like inverse square. So the loss is much smaller. So therefore, suppose you have a satellite here, okay, some satellite here. So this satellite, it can have some photonic devices. It can prepare entanglement. It could be something like this entanglement source. Okay, suppose it can have some photon. It can excite that photon to you get 2 entangled qubits, and you can transfer 1 qubit to this detector and ground station antenna. It can transfer another one to here, and then they will be coupled. So during this entire region, your loss is much smaller. So there is a higher chance that your qubit will be transferred successfully. So this is how satellites will play a significant role in quantum internet. You will have multiple satellites which can talk to each other in the space, and in parallel they will be also moving around the earth. So there are several challenges. So these detectors, they should be able to see those satellites. Okay, they can receive signals only if they are within certain angle. Okay, and future quantum networks will be heterogeneous devices, some ground devices, some space devices. Now how do we analyze those quantum networks? Now if you take any regular quantum network, essentially you need to now apply some routing, path selection, and so on. Okay. So this is some quantum network. How do we create entanglement for A, B, and B, C? Okay. And this node is switch. This is called quantum switch. Why? It is connected to more than two links, and this is called there is no repeater here. But if there is some, say suppose some repeater here, this is called repeater. It is connected to only 2 links. Okay. So how do we use these devices effectively, and allocate their resources so that we can distribute entanglements for these applications? So that is where quantum networking will play a role. Okay. Scheduling. Suppose if you have multiple applications with different demand, now how do you schedule them? So we need some queuing, probability theory, optimization, everything will come into picture. Okay. So once we exploit these quantum mechanical properties, so analyzing them is similar to classical networks, except that we need to keep in mind these quantum mechanical operations. Okay. So I will stop here. I think we need to take a break here. Okay, we can get started. So our current devices, and in near term, maybe in 10 years, 15 years, so mostly we will be using teleportation, and most important we will be using entanglements for communications and so on. So they also talk about second generation repeaters, which essentially they can apply this quantum error correction. Okay, so currently this error correction is still in initial stages. Suppose if they can apply quantum error correction, essentially the rate of entanglement generation will improve. For example, sometimes when we are creating entanglements, they are noisy. They can correct these error correction things. Codes can correct those errors, and therefore it will improve the speed of communication. Okay. So next, I will highlight how distributed quantum computation can be benefited from quantum networking. So now, okay. So companies, for example, if you say that I want to develop quantum networking algorithms and so on, to connect to nodes located in different countries, then they are not interested at all. Why? Because they say it is futuristic. It takes probably 30 years, 40 years time to connect to nodes available in different countries. But the most important application is actually distributed quantum computation. So we can motivate quantum networking by considering it as an important application for distributed quantum computation. Why? So in today's quantum technology, different companies are using different qubits. Some of them are using photon qubits, some of them are using trapped ions, nitrogen vacancy centers in diamonds and so on. But in all those cases, in all the technologies, you can only have hundreds of qubits in each quantum processing unit. Okay, so in practical systems, we can have hundreds of qubits. Okay, hundreds. We can have hundreds of qubits. Okay, like 500,000 and so on. Okay, so there are some challenges. What are the practical challenges? So these qubits, you need to control their environment because they are very delicate. So if suppose if temperature changes, then their state will change. If some electronic magnetic field is there, then their state will change. Okay, so you need to control their state. Okay, and so you need some cooling systems. Okay, okay, so cooling systems, suppose if you want to prepare a single quantum computer that has 500,000 qubits, then you will need to use some cooling system that is as big as, say, some football stadium or something. So very big. So you cannot have cooling systems that control the temperatures, like cryogenic cooling temperature or something, like very low temperatures. Okay, so you cannot have practical cooling systems to design large quantum computers. The next is, yes, yeah, because the temperature means it takes some energy, right? Suppose if you are sending photon in space, it will disturb their energy. So for example, you have 0 qubit, it's in ground state. If you hit with some sunlight, its energy level might increase and it can reach to one state. Classical bits, they use different wavelengths. So different wavelengths, and also, so photons, it seems they will have some noise. If you have sunlight in the environment, it will go through some noise. Okay, so it depends on qubits. The type of noise you will get depends on what qubit you are using. They are using some superconducting qubits, which are some atoms of some particular materials, which are used for quantum computation and so on. So they require very small temperatures. Okay, and also if you are using quantum computers, so all control information is exchanged in classical internet, is exchanged via classical internet. Okay, so within a single quantum computer, you will have several fiber optic cables which are used to send signals, classical bits, from one qubit to another qubit and so on. So if you are placing hundreds of fiber optic channels, when you are directly transmitting qubits on those channels, there will be some interference between different fiber optic channels. So you cannot place, there will be some limit on number of fiber optic channels you can place close to each other. So because of all these challenges, and then some other challenges that are there in hardware systems, so they claim that they can only prepare quantum computers that will have hundreds of qubits. like 1000, 500, 200 and so on. Okay. But most applications where we claim that quantum computers will have an advantage over classical computation, they require millions of qubits. Okay. So we need millions of qubits in important applications. Okay, for important applications. Right. For example, that Peter-Schwartz algorithm to factor large integers, they will require at least 1 million qubits. Okay, but you cannot have such a single quantum computer that will have millions of qubits. There are some practical challenges. Okay. So now the only way and the only hope is to have several small quantum computers and connect them through a network and use their capabilities to solve bigger problems. Okay. Yeah. So essentially QPU is like quantum computer. It can be one QPU, like multiple QPUs and so on. Like 100, like around 100 qubits, and then we need to use a network to connect them. So these practical challenges.
Okay, system.
So yeah, so in a single chip you cannot place several wires. Some physical constraint, and then some cooling. You need to control their temperatures and so on. Okay. So this is a rough idea on why we cannot have large quantum computers. Okay, or large chips, which will have millions of qubits. Okay, and also they have some quantum error correction challenge. They cannot correct them and so on. Okay, so how does now when we prepare quantum computers, right, it can have multiple QPUs. Like suppose if you take GPU supercomputers, within a single computer you will have several processing units. So you can have like that. Like if you take data centers, right, you have several servers which are connected through a network. Okay. So similarly in quantum, we need to develop quantum data centers, which are essentially QPUs that are connected through a network. It could be something like this, or it could be some switch connected through a network. We need to come up with different topologies. Okay. So all of these are QPUs, QPU1, QPU2, QPU3. Okay. Suppose each of them have 100 qubits, then using a network, we can make this network act like a 300 qubit quantum computer or 400 qubit quantum computer. Okay. So we can combine their resources using a network. Mm-hmm. Yeah, yeah. Ideas means, yes, they are still developing them. So okay. So but ultimately, if we want to solve important problems using quantum computations, we need to have data centers, quantum data centers. Maybe they will have 100 QPUs, 1000 QPUs. We don't know. It is still need to be developed. For example, Cisco has written some paper recently on importance of quantum data center design, and they have come up with some algorithms. Okay. So how do we, for example, if you have some big algorithm, right? So this is a large complex algorithm, and each quantum QPUs, they do not have capabilities to solve this algorithm. So you break this into 4 parts. Okay, and you can allocate each of the parts to different QPUs, and they can solve these sub problems, and then you can combine their results and try to get final output. So if you have 1 QPUs, you cannot solve this problem, but if you have 4 smaller QPUs, you can try to solve this problem using quantum networking. Okay, any ideas how we can use quantum networking to solve this bigger problem? So again teleportation, right? You solve, you get some result here. Okay, so one part is solved here, or another part is solved here. Now we need to combine those results. So what do? We need to teleport these results to here, and this guy can combine them and give final output. And you can transfer results directly on this cable, fiber optic cable, but there is some chance that that result could be lost. So you do not want to waste your computational resources, right? You know, you have spent a lot of resources here, you got some partial results. If you directly transfer them, there is a chance that they can be lost. And also there is, as I mentioned, there is some crosstalk. Okay, so there could be some interference on the channel. Okay, so it can lead to some loss. So the best is to do teleportation. If you have teleportation, there is no transmission, therefore results will reach here with high chance. So teleportation is one way. Okay. So therefore it is very important to understand how to distribute entanglements by taking how distributed quantum computing systems are operating in real systems. We need to understand their behavior, their architecture, and so on, and then we need to develop networking algorithms to connect these quantum processing units. Okay. So for example, in this case, this is like a switch. How do we develop switching scheduling algorithms to connect different QPUs? Suppose if this switch is operating at suppose if the switch is not operating at high speed, then you are going to waste these QPU resources. The moment these QPUs are ready to talk to each other, your switch should build connection immediately without much delays. Okay. And also sometimes when we are storing these partial results in QPUs, those results also will be lost with time, because this every quantum state is going to interact with the environment and noise and so on. Their state will decay with over time. Okay. So in practical systems like this that is called coherence time. The coherence time is like milliseconds, microseconds, depending on qubit property. There are qubits for 1 hour which have coherence time of 1 hour and so on. So networking, developing high speed networking algorithms is very important for distributed quantum computation. Okay. And there is another application which is application of remote gates. Okay. Are distributed gates. For example, there is qubit here Q1, there is another qubit Q2 here. You have an entanglement psi. You can apply a gate on these two qubits, although they are not in single location. For example, there is a quantum circuit. Okay, using entanglement psi, you can apply remote C0 gate on qubit Q1 and Q2, even though they are not in single QPUs. So even for that distributed quantum gate execution also, we need entanglements. Okay. So now, for example, if you want to combine this QPU and this QPU, there is a path selection, and there will be, suppose if this switch has some resource constraint, whether to match connect these two QPUs or these two QPUs, how do you decide? Okay. Mm-hmm. Mm-hmm.
I transmit.
Mm-hmm.
So here if I have to transmit one photon, what is the bandwidth requirement maybe?
So they have some photon wavelengths, telecommunication wavelengths or something. I am not sure exactly, but there is some particular wavelength requirement.
Okay, wavelength is okay, fine. Okay, in terms of hertz, okay, fine.
Yeah. Okay. So this is why quantum networking is very important, and also we have we can store temporarily qubits in some memories. Okay. So when you are doing some operations, you got some partial result, you can store in memories. Now you need to exchange these results, and these qubits are going to expire soon. You know, how do you use those qubits before they expire? You know, can you come up with networking algorithms so that this distributed quantum systems executes these algorithms with minimum delay? Okay, so the networking terminology, suppose if you are what is the optimal algorithm to minimize the average delay when you are serving multiple applications, considering this type of quantum computation algorithms. So all these are challenges, these are all new ideas, so still people are exploring. So there is not much analysis, it's all because people who work on these things are mostly physicists, hardware community people who do some experiments, apply some software and so on. So but from networking community we need to come up with analytical models for these systems. Yeah, so they are kind of related. So I think no one has explored, but age of information is similar. For example, every qubit will have some lifetime. So if you use that qubit within certain time limit, then it will have better impact in applications. So age of information type of ideas are useful. Yeah. Sorry, what? DRAM, random access. Yeah. Mm-hmm. Mm-hmm. Yeah, so when you consider like quantum memory management, so ideas could be similar. So here in quantum, the main difference in between quantum and classical is that quantum information will have some lifetimes. So you need to use that quantum information before that lifetime exits. Okay.
Different qubit and then store it, right? Like you can keep
Yeah,
doing
that's what
it.
people do.
Okay.
And then you can also apply some operations to improve its quality. That is called entanglement purification and so on, which we didn't get time to explore the last topic. But when you have low quality quantum states, like entanglements in particular, so we can combine different low quality entanglements using some quantum circuit, and then we can try to produce single high quality entanglement. So that is also an important factor in quantum networking.
Nice. And like sometime in the middle, you were also talking about this error correction and those things that are done. Is it similar to like classical error correction?
Ideas are similar, but quantum error correction is much more challenging.
Okay.
Why? Because this in superposition, when you say alpha and 0 plus beta 1, right? So in classical, we have only 0 or 1, right? Lower energy and higher energy. Suppose 0 to 0.5, if signal level is in between 0 to 0.5, you always go back to 0. If it is 0.5 to 1, you always go back to 1. So correction is easier because it's only amplitude. But in quantum, we have phases also. In these complex numbers, we have phases also. So essentially, if there is some noise, for example, if there is a qubit, okay, along this direction, theta, even a small perturbation can go to like this direction, theta dash. And both of them are, valid quantum states. You don't, maybe you received this qubit, maybe you thought that this is the correct one, because this is also a genuine qubit. This is also a genuine qubit. So handling phase changes is very challenging.
Nice.
So error correction in quantum is much more challenging. So I mean, in conclusion, still quantum networking, quantum communications is still in initial stages, And there are very few people who are working from electrical engineering or computer science background who work on, say, networking and communications in this area. So it is good to start looking at this topic. So I will conclude here. Thank you.
Thank you very much, Professor, for taking out time to come to India and giving us such a wonderful tutorial today. So as a token of our appreciation, we would like to thank you a souvenir from Professor Srinivas Sain.
Thanks all for coming to this program.
Thank you all.